Hello everyone. Today we'll be presenting our CariSurg 2025 project on the cost-effective gastroscope for cancer screening and showing you what work we did over the summer. But before we begin, I'll give you a brief introduction of ourselves. So, my name is Nehal Wadwani. I am from St. Lucia. I am currently studying at Columbia University pursuing a degree in mechanical engineering.
And I am Justin Suknanan, a recent graduate from the Electrical and Computer Engineering program at the University of the West Indies in Trinidad and Tobago.
So why is this relevant and important to us? First, I'll define what a gastrointestinal cancer is. It is a growth of malignant cells along your gastrointestinal tract, that is, your esophagus, your stomach, your duodenum, etc. And, in fact, stomach cancers were one of the top 5 most prevalent types of cancer in the Caribbean, leading to approximately 13.2% of all cancer deaths in the Latin American and Caribbean region. Early screening is very vital for these types of cancers since symptoms only become apparent when tumors have advanced. Therefore, it is very vital to increase survival rates through screening. And currently, the gold standard for these cancer screenings is gastroscopy. But it is very expensive. It requires indirect and direct maintenance costs. It requires specialist training, as well as is very bulky and cannot be brought into remote areas. Therefore, the Storm Lab decided to come up with a solution, the Belloscope.
We propose the Beloscope, which is a soft continuum robotic solution that aims to be a low-cost alternative to traditional gastroscopy. So I use some terms here that may be new, so let's break this definition down some more. So when we think of traditional robotics, we picture rigid components that prioritize strength, like this robotic arm, this car, or even this robotic dog. But when it comes to soft robotics, the focus is slightly different. We're interested in robots made up of flexible materials that comply with their environments, but at the same time are strong enough to execute its particular task, such as gripping an object or navigating a space. And continuum robots refer to robotic structures that can achieve continuous bending, like those shown below. And it's actually interesting to compare the positions that these continuum robots can achieve, which is any position according to its bending radius, to that of our rigid robotics, which can only achieve specific positions that are based on its joints. So putting this all together, this is why the Beloscope is classed as a soft continuum robot, because it must be made up of soft material that is gentle on the internal tissue, but at the same time achieve continuous bending to visualize the gastrointestinal tract. So now let's speak operation. The Beloscope is made up of 3 main parts: the user interface, the actuation system, and the endoscopic tip. The user interface is a multi-backbone handle that comprise of these cables that are connected to the pistons on our syringes in the actuation system. And the manipulation of this handle extends or retracts these pistons, which in turn creates a pressurization or a depressurization downstream to our parallel bellows structure at the endoscopic tip. And it is this change in pressure that results in the change in orientation of our endoscopic tip. And together, this is how our system allows clinicians to perform gastroscopy by manipulating the handle and observing the gastrointestinal tract.
Though this design was a great step forward, there was some improvements to be made since the user handle was reported to be stiff and the system needed to be disposed after every use, including pricey electronics in the tip such as the camera. Seeing these complications, we worked on the following improvements: a new detachable tip design, replacing the actuation system with pneumatic pistons, and redesigning the user interface with a thumbstick. This visual shows a high-level overview of what our new system would look like. A user would move the thumbstick to an XY position, which would then be correlated to the linear actuators through a microcontroller. This would allow the linear actuators to compress or extend the pistons by a certain length, allowing it to pressurize or depressurize the bellows, resulting in a bending and plane angle, allowing the camera in tip to get a full view of the stomach. Our proposed design was 2 printed circuit boards connected via a circular connector as seen in the video below. The top PCB houses the components of illuminations, such as the LEDs and camera, while the bottom PCB remains fixed to the distal end of the endoscope. Together, it provides a strong and reliable wired connection. To protect these electronics, we designed a push-fit silicone connector. The design ended up being around 9.7 millimeters in diameter, making it small enough for standard endoscopic procedures. For the actuation system, we replaced the syringes with pneumatic pistons that are more robust and can be sterilized between uses. They offer safe but enough pressure to establish a good range of motion and are functional with most linear actuators since they only need a force of 8 to 12 newtons to be displaced. The pistons were then coupled to the linear actuators and bellows as seen in the video. As you can see, one bellow is compressed and the other two follow the path of motion, allowing various bending angles. On the right is an image of the range of bending angles a single bellow can produce with this piston. Finally, we now have all our moving parts, but they need to be able to move as one uniform system. If you remember from our proposed system slide, there were many components to take into account, from controlling the thumbstick, to the linear actuators, to the pistons. This can get very complicated and messy quickly. To combat this, we treated the entire actuation system as a black box and worked on investigating the relationship between the tip position and the actuator inputs.
To determine this relationship, we perform characterization, and this is done using the setup shown. So to the right, we see our actuation system, and to the left, we see our endoscopic tip. And the position of our endoscopic tip is tracked using electromagnetic sensors. So together, this system allows us to activate the pneumatic pistons and observe where our endoscopic tip moves. So the first experiment we performed was single bellow characterization, where we activated one bellow at a time. And we observed that activating each bellow results in the tip following a particular path, each of these paths being 120 degrees apart from one another. So it's actually intuitive to think that combining the activation of multiple bellows would allow us to achieve positions anywhere between these paths. And in multi-bellow characterization, that's exactly what we determine. By activating different sets of these pistons, we achieve approximately 360-degree rotation and bending angles up to 135 degrees. These parameters are really useful because they indicate that a large area can be visualized during a gastroscopy procedure. So our next steps would involve actually building on these characterization experiments and obtaining a data set that relates belloscope positions to actuator inputs. And this data would be really useful for integrating our thumbstick to our system. And this would allow us to obtain our final prototype and eventually move on to clinical testing with our belloscope system. Thank you, and this brings us to the end of our presentation. We thank you very much for tuning in, and please remain connected with the CariSurg team through our website and various social media.